Let us use the math sheet to examine the wagon wheel problem. Here I've set up the math sheet, and notice that I've defined the radius of the wheel and the frequency at which it turns. We're told that the camera flashes 30 times per second, so I've set down a t-axis, a time axis here, with an increment of 1 over 30 and computed the usual time subdivisions. I've also defined my x and y coordinates for a point on the wheel, and notice that these include some absolute references. For example, here I point to the value of the radius that's contained in column B, row 2, and also the frequency that's contained in the same column in row 3. The spreadsheet will understand the meaning of pi, and moreover, I'm pointing to the time C1, which is the time corresponding to this x value that I'd like to compute in this box. So I've set up my spreadsheet to plot the x and the y values. In order to understand this problem, it might be helpful to actually plot finer increments on the time axis and plot both the x and y coordinates just to see that actually this wheel is turning quite fast. And so I've also added a second time axis, which is much more finely subdivided, and I'm computing the same x and y coordinates. So you'll notice that the formulas are basically identical, but now I'm going to compute them with a much finer time subdivision. Let me look at the graph. So on this graph, I have already plotted the x coordinate on this very fine time increment. And you'll notice that here on the range of x goes from 0 to 0.2, we see that the wheel has rotated many, many times and performed quite a number of cycles. I could, of course, to this add the y-coordinate of this rapidly evolving wheel simply by adding the time coordinates F1 to 200 and H1 200. Let's do that in red so that we see the two graphs, one alongside of each other. So this really shows us that the wheel goes around quite quickly, although for what we want to do next, really this y-coordinate is going to be undesirable. So let's just get rid of that red graph for the time being. Okay, now to that actual behavior that we see on the graph, let's add the apparent behavior that's obtained from using the camera flashing. So to this graph, I'm going to add another XY plot, which will give me what the camera sees. So here I'm going to use row C and D. In other words, I'll take the values in, and let's check how many values we've got here. Basically, we've got a total of 30 or 31 values that the camera sees. So let's go ahead and add C1 to 31 and D1 to 31 on this graph. Let's make the dots visible here just so that we can see the actual coinciding of the camera flashes with positions on the actual wheel. Furthermore, in order to see this on a slightly broader x-axis, let's edit the graph parameters and look at this up to a maximum x value of 1, just so that we see the whole progression. So here we see both the fact that the wheel goes quite quickly and also that we're seeing only a few points on it as the camera rolls on. Okay, we've made the point about the actual and apparent velocities, or at least the actual and apparent motions. Let's at this point get rid of the rapid cycling just so that we can see our graph a little bit better. And instead, let's add the y component, the y coordinate of what the camera is seeing. So edit, or rather new xy plot. And now the xy plot is contained in row E. So we're going to, again, write C1 dot dot 31 and E1 dot dot 31. Click OK. Let's make the dots bigger again so that we can see them. And here is our y coordinate as seen by the camera. Okay, now what is it that we're being asked to find here? We're being asked to find at the instant that the y coordinate hits the top of the wheel, which is this point right here, we want to find the velocity or the speed at which the x component is changing. In other words, we're really after the slope precisely at this point, which coincides with the time at which the y coordinate is as high as possible. We observe from the graph that the y coordinate is approximately 0.5 at this point. Let's go back to our spreadsheet and focus attention on the camera and look for the time at which the y coordinate attains the value of 0.5. So we need to look down a ways, and we see that that occurs right here when t is equal to 0.833. And now what we'd like to do is compute the corresponding slope precisely at this point. We can approximate that slope by looking at the points on the x coordinate at the adjoining time points. So for example, we can take these two x coordinates and divide by the corresponding time lapse. Okay, let us focus attention then on these points, and in any one of these cells, let's compute that ratio. So in this cell, I'm going to write D27 minus D26 divided by C27 minus C26, and there we go. So there we have it. That is the slope of the secant line at this point, or which is a good approximation or a reasonable approximation of the slope of the tangent line, and therefore of the velocity of the x component.